In this video, I'll go through some examples of exponential functions. So we can write an exponential function in this form: f of x equals a times b to the x, where a is the initial value when x equals 0, and b is the multiplier. And if b is between 0 and 1, we have an exponential decay function. So as x increases, the value of the function decreases. Whereas if b is greater than 1, we have an exponential growth function where as x increases, the value of the function increases. We can also write the function in this form: a times 1 plus r to the power x, and r here is the rate of increase or decrease expressed as a decimal. And now if r is between minus 1 and 0, we have a function that decreases as x increases, whereas if r is greater than 0, we have a function that increases as the value of x increases. One thing to note here is if b is 1 or if r is 0, then we don't really have anything interesting, because 1 to the power of x is just 1, and so the function is just the constant a. Let's run through some examples. So let's start with an example representing sales, for example. So the sales starts at time 0 at 10,000 units and increases by 5% every time period, where x represents the time periods. So the function here is written f of x equals, so the initial value 10,000, and then the multiplier b is written as 1 plus r, where r is the rate of increase expressed as a decimal. So r is 5%, so as a decimal that would be 0.05. So 1 plus 0.05 is 1.05 to the power x. So let's do a few examples. So for example, after 1 year, what would sales be? Be 10,000 times 1.05 to the power 1. So 1.05 to the power 1 is just 1.05. 1.05 times 10,000 is 10,500. So sales have increased to 10,500 after one time period. Let's do another example. What about after 10 years? What would the sales be? So now we'll have 10,000 times 1.05 to the power 10. So we're multiplying by 1.5 for each time period, so we're doing it 10 times. And then if you do that calculation on a calculator, you get 16,289 to the nearest whole number. So that's what sales would be expected to be in this scenario after 10 years, or 10 time periods. Okay, how about a decay function now? So let's do f of x starting at 1,000 at the beginning of the time period, and the starting time period, every time period after that, the amount decreases by 12%. So 12% as a decimal is going to be minus 0.12, and so 1 minus 0.12 is 0.88. So there's our exponential function. And let's do some examples. So after one time period, we'll have 1,000 times 0.88 to the power 1, So that's 0.88 times 1,000, so 880. So for example, if this represented the decay of some radioactive substance and the starting weight was 1,000, so after 1 day, say, if it decreases by 12% every day, we're down to 880 after 1 day. What about after 7 days? So it would be 1,000, and then we're going to multiply by 0.88 7 times. And if you do that calculation on the calculator, you get the weight is down to 408.7 after 7 days. Okay, what about an exponential function if we're given the value of the function at the initial value, so f of 0, let's say it's 120, and after 5 time periods, when x is 5, we're up to 230, and we've got an exponential growth function, and we just need to figure out what the function looks like as a formula. So the way that we can solve this is, let's write down what we know. So we know the value of a, it's 120, but we don't know the value of b. So this is what our function looks like. So for example, if x was 5, this would equal 120 times b to the power 5. But we're given that value. We were given the value after when x equals 5 is equal to 230. So now we've got an equation with one unknown, b, and we can solve for b. So if we divide both sides of the equation by 120 and then take the 5th power, or the 5th root, we're going to have this equation here. So we can write this two ways, with this radical symbol here representing a root, and then the 5 represents the 5th root. Or another way to write this is with 230 over 120, and then we can raise that to the 1/5 power. And then using our calculator or using a computer, we can calculate this, and it comes to 1 point, and it's good to go to at least 4 decimal places here so that we're as accurate as possible. 1.1390. Okay, 1.1390. And then going back to our equation here, our exponential function looks like this: 120 and then 1.1390 to the power x. And it's a good idea to check our number here, our numbers in our formula, to make sure that we're getting back the information that we started with. So let's figure out the value of the function when x equals 5 and hope that we get 230 as the answer. We should do, assuming we haven't made any calculation errors. So 120 times 1.1390 to the power 5. If you do that on a calculator, you do indeed get 230 to the nearest whole number. Okay, and finally, let's do an example where we're given two values of the function, but neither one is the initial value at x equals 0. What do we do in that case? Okay, so it's a little bit more complicated, but it's essentially the same kind of process. Let's write down what we know. So f of 3 as a formula would be a times b to the power 3, but we're given the value 5 in our initial information for this question, for this example number 4. So I could rearrange this and solve for a. So a is going to be equal to 5 divided by b to the power 3. Okay, what about f7? We're given that number as well. So that would be a times b to the 7, and we're told that that is equal to 24. So let's plug in this value of a that we just derived into this equation. So now we're going to have 5 over b cubed, that's a, times b to the 7 equals 24. So let's simplify that. Let's think about what this means. 5 divided by b to the power 3 times b to the power 7. So if you think of b to the power 7 in the numerator, we're going to have b times b times b 7 times, and then in the denominator we've got b times b times b just 3 times. So 3 of the b's will cancel in the numerator and the denominator, and we're going to be left with 4 b's in the top. B times b times b times b. So I could write this as 5 times b to the power 4 equals 24. And then the final step is to solve that equation for b. So we'll have b equals the 4th root of 24 divided by 5. And I'm going to write that in this form. 24 divided by 5 to the power 1 over 4. And we can calculate that with a calculator or using the computer, and it comes to, and again it's good to go out 4 decimal places here, 4.802. Okay, we're not quite done yet. Let's just get rid of that so I can use that bit of space. We need to figure out what a is. We figured out what b is, but we don't know what a is yet. So let's go back to this equation here, because there's an equation for a right there. So a is going to be 5 divided by 1.4802 to the power 3, and using a calculator we can figure that out as 1.5417. So finally we have our function f of x equals a, 1.5417, and then b, 1.4802 to the power x. So there's our exponential function. And we could check, again it's always a good idea to do a check at the end to make sure we haven't made any calculation errors. We could check either for the value of the function at x equals 3 or at x equals to 7. Let's just do the value at x equals 3. And so what we would do is plug in the value 3 into this equation. So we'd have 1.5417 times 1.4802 to the power 3, and if we do that on the calculator we get 5, which is what we want because that was the information given at the beginning. So there's a few examples of exponential functions.